Okay. I will present you reverse engineering on advanced microcontroller with high-speed peripherals, especially USB3 super speed. So let's introduce me again. So yeah, I work mainly on embedded hardware and firmware with open source software, of course. I worked on, I created RISC-V, R0, R2, and Mini a few years ago, which still are available. And I worked with Nicolas Oberly on Hydra Bus V1 with some extension like Hydra NFC V1, V2. And the new hardware I will present you is Hydra USB3. And also, I presented a few weeks ago with Nicolas Hydra SCA Liaison, which is special hardware for side channel attacks. Okay, so let's start. And why this research engineering project? So, like everyone know, since a few years we have some chip shortage problems on a lot of, or even all microcontrollers. So I was searching something which can be found, okay, something available, and as everyone knows, RISC-V is quite interesting because it's open hardware. So I say what we can find with interesting features different than STM32, for example, or NXP microcontroller, as they have always the same type of peripherals and everything is always the same on microcontroller. So let's see what I have found. So it was the WCH CH569. So it's done by a Chinese company, which was owned by Winchip Head. So it's not well known because it's everything is in Chinese. You will see after. Okay, so the interesting point is the RISC-V is 32 bytes with 120 megahertz, so it's quite fast. It's use a proprietary RISC-V architecture, but it's very similar to the open one with IMAC. So there is basically integer instruction, integer multiplication and division. It supports also atomic instruction and compressed instruction, which is quite interesting to have compact code and a small binary. So other interesting point is a fast interrupt, which is driven by hardware to save and restore the registers using a non-standard attribute in GCC, as they have done a custom GCC fork, which is not open source today, so we can insist on that, as they must provide. It's another point. So there is also 60 byte SysTick, so it's a cyclic rate, so it's also very interesting to count the cycles. So now let's see the interesting point today is mainly USB 3 and USB 2 PHY and integrated. So it's quite rare to see such feature, especially it really go to 5 gigabits per second on a microcontroller, which is quite low power. And we have also something I have never seen before in a microcontroller, as we see often such in the FPGA. It's a SerDes with a built-in fee also, which can go up to 120 gigabits per second. So it's quite fast and interesting to have such in a microcontroller. And we have also standard peripherals, which are quite fast, as SPI, which exceed 50 megahertz, and UART also quite fast. And you have option to have Ethernet MAC with gigabit, but external fee. And another amazing thing is a high-speed parallel interface, HSPI, which can go up to 3.8 gigabit per second with a bidirectional bus, which can be configured to 8, 16, or 32 bits. So it's a quite amazing thing also. Mainly to interface with external external world, mainly FPGA, because it's quite custom. So we have also interesting point is eMMC, SD card, SDIO, which go up to not far than 100 megahertz and 8-bit. And also, I don't think about that, but Nicolas do a presentation. It has also encrypt core with SM4, which is quite unique, and AES, of course. So let's see how it started. So yeah, when I started to check that MCU in January, in fact even before, I was starting to check this amazing chip. There was no any one official dev board available because all is in Chinese, you see. And there also the specification is quite interesting if you can decrypt such mess. So yes, it's like that. It's full Chinese. So maybe I should have learned Mandarin. I don't know. So let's design a board because we cannot have anything. Okay. So I will do my own board and also add some convenient things because there, you see, it's not the best and it's quite big. So what I do, like always, I'm using a KiCad design tool, which is full open source and very nice to design some PCB and schematic, like we see there. So I started by a POC evaluation with 4-layer PCB because it's mandatory for USB3 or SerDes to have a good signal integrity because it's quite very fast. So you cannot do that on two layers. As you need also impedance matching, we will see that later. So what I do on this reference design, which was done in Altium, okay, as KiCad 6, even 5, I think, I just converted the schematic there. It's also by hand. I changed a lot of things, but I converted it. It was quite nice importing, and just replaced something which was not required, like a DC-DC step-down converter, 1.2 volts. I remove it because it was not required. I don't know why they add it, but I replaced some DC-DC step-down converter by some low noise LDO with low noise to have a best the cleanest possible power supply, and also use the best possible crystal because it drives the USB3, SerDes, and high-speed bus, and it's always better to have something clean. Okay, so let's check the first board. Like you see, the first board was done at GLC PCB. So using their impedance matching GLC 7628. And what was the challenge was to match the differential impedance of USB interface that we can see there. USB 3, USB 2, everything is there. We see. The SerDes also is 100 ohm impedance to match. So it's quite short, so it's not really big issue. Okay. And at the same time, length the match of the trace for the HSPA connector there. So because this bus can go up to 120 megahertz with 32 bits. So it should be as best as possible. So there we see a thermal camera photo to check what happens with the LDO. It's quite hot, about 40 degrees, but the MCU, like you see, 33 degrees. So it, when you're running at USB 5 super speed at maximum data rate, so it's quite cold, 23 degrees, when you have 25 degrees temperature. Okay. So let's continue with the second iteration. So there, the objectives, the goal was to miniaturize the board and to add more features, like you see, the different steps. So full redesign from scratch. Now the board is 6 by 6 centimeters with top mal pin and bottom femal pins, like we see. So it's very convenient to connect two boards together and to communicate with two boards. We'll see after. And there we have SPI, for example, UART, and some GPIO. And you have tons of possibility to measure the current and things like that, or even to reset the CPU there. Okay, so we see the back, and we see the final, the first board, okay, which was working fine at first time. So now we see the third iteration. So it's mainly the Hydra USB3 like it exists today. So what I have done also some optimization, some improvements, mainly on ESD. As you know, if you have some ESD, you can kill the CPU. So I like to have military grade things. Yes, it's more than 15 kilovolt protection there, and also there on the USB. The VUSB is the power from USB, so there is no risk to damage the chipset when you connect your USB cable inside. I have also changed some buttons to are more accessible on the border, and I have had a lot of ground, as it's very convenient to plug a logic analyzer, so you can solder some pins there, and you can spy all the pins. Okay, so the final board is there. It's the one produced today. So like you see, it was finished in end of May. So let's see a bit pin assignment. So like you see, there is huge pin there on G1. It's for the 32-bit bus, which can also be configured as SPI1 if you don't use some features. You can use both at the same time. You have also the CRDS there. There you have SPI, and we have some current measurement shunt there, power LED, reset button, and the USB 3 connectors. Some jumper also with user button to be configured by software. Okay. So let's start the hard part. It's reverse engineering. As I know, a lot of you like to reverse engineering stuff. So how it starts? It starts with that mess, all in Mandarin, like you see. Oh yes, it's very interesting. We don't know, we don't understand anything, just some keywords, USB 3. Okay, it's a full spec there of the USB 3, you know? One page. The CRDS is the same. And what they have done after, because there is a lot of complaint by some user like me, they have write an English datasheet. Wow, very nice. It's just a translation, nothing more. And you see, please refer to and call the provided subroutine library for specific application. So what they say there, it's only blob everywhere and no any documentation. No details, this is fine, okay, like says dog. So now let's start the hard part. So how to reverse engineering RISC-V and what are the tools? So far there is GIB decompiler. Never tried that because its evaluation version is quite limited. We have IDEA Pro, like you know, everyone, but RISC-V support is quite limited. There is no decompiler, so it's a major point to reverse something, because the objective is not just to reverse, but to rewrite the code. So we need also to extract something. So three alternatives supporting RISC-V. So Radar 2, like everyone know, but what's the problem? No decompiler. Okay, so the last solution, GreHack 11, the 10, and it supports RISC-V decompiler. So it's quite amazing, and it's fully open source. It's created by NSA, like everyone know, since few years now. So we have an extract of ELF loaded, and you see the code is quite nice in pseudo C. So the first reverse engineering will be focused on SerDes. So it's a serializer, deserializer. It's amazing because it's only 2 wires and it's quite robust. Okay, and what we can find online, it's just someone we do a clone of the repository which disappeared from the WCH. Because their examples, they remove the SerDes. I don't know why. There was probably something they don't want to show to everyone. So what to do is open source everything and remove this crappy blob. It's a static lib they provide, and you don't know what happens inside. And also, it's quite limited. We'll see after. So support, the objective is to support different SerDes speed and even improve the driver, and to have it fully open source. So let's start with how to reverse with RISC-V. So first, you have a lib SerDes, the blob. You can start like that, and you open it, and you search serdes.o, for example, and you have the function, okay? You just have the name, and there, like you can see, the RX in it, for example, you have the pseudocode there. But mainly, it's full of register and you don't know what happens there. It's the main frustration when you see such. So let's start. And in my case, I took the ELF, I rebuilt the lib, and with different links everything to the ELF, and I started to reverse. So first problem is GitDry is not perfect, okay? Why? Because sometimes it misses some crucial steps, like this one, you see? It's not there. There is no 57 there, access. So what happens? It's missing a peripheral access. And such is quite mandatory because you cannot do other access after that because it's like an unlock of the peripheral. So, okay. So we see that. If you read carefully the assembly, the disassembly code, you can understand sometimes the pseudo-C code is not perfect. Okay. So we'll see now how to avoid that. This crazy bug, because you can miss a lot of access. There was only one, but it's quite random. So the magic come with SVD loader. As I don't know if you know it, but it was originally for ARM microprocessor. It just charged SWD, system view description. So fortunately, we have one. It was hidden in Moonriver Studio community, and it provides a lot of interesting things. Like you will see, you have a lot of peripherals with are mapped, so that will help us a bit. Even USB super speed, but it's quite basic. Okay, we will focus on USB super speed, USB 3, and SerDes. You see, there is also some range. So after that, what we have now? So before we had such mess. No, in fact, this one is a fix. You see the peripheral access there, and I apply the SWD, and there we have clearly something more interesting with peripherals, with safe access, with all the data, and we see even a SerDes analog COM file. Okay, so such things need to be reversed also, because they don't provide any things about that. So we will continue the reverse engineering on this small function that now is more clear, as we see some access. And the hard part will be to read the datasheet, not the datasheet because there is nothing in the datasheet, the header, because they have provided some headers, and we can reverse all that mess. And to finally have this clean code at the end, which, and even some improvement, because there we have, okay, we see clearly what happens in the SerDes control. And even there, we know that it's a SerDes PLL. We wait it's ready when it's configured. Okay, so now let's do the same for the TX, the transmission. So it's the same process, we reverse again, and we reverse that X value to something more clear. And even to, as we know, understand how it works. Okay, the fee reset, link reset, and everything is quite clear. Fortunately, because they have such define. They avoid to remove them, so it helped me a lot. Only this one is undocumented. So, fortunately, I don't need to change it, to change the speed. We'll see after. There. The PLL frequency, it's what I had as we change the SerDes speed to different frequency, which was not possible with the blob. So there you see the SDS PLL frec, which is a parameter, and we can configure the SerDes from 180 megabits per second up to 1 and 1.4 gigabits. Even if it's out of spec, it works. So you see, I did also during debugging a code improvement to wait TX is ready at the end of the configuration, because you can have some erratic bugs after that if you don't wait and you try to send some data. So there we reverse also the wait takes done to wait when we have sent some data over SerDes. The same, also code improvement on TX ERQ to clear the interrupt flag after the send. It's always better. So there we have default speed. Oops. Default speed of 1.2 gigabit per second, which can be changed now. So the SerDes is based on LVDS, only 2 wire. It's a differential pairs with. Okay, you see there. It's a built-in fee. It's very interesting because you don't need any other components. Everything is integrated. And it's done in the fee, the 8B, 10B codec, plus CRC check. And also, it includes, after reverse engineering, a CRC32. It's from SATA specification. So now, let's see an example. Okay, when we have rewrite everything in C, and the driver is done, it's available on GitHub. And also the example to use it to transmit or resave with 2 boards. So for example, you have a board which do the TX, this one the RX, and we connect the both. And we can exchange some data at quite fast speed, like we see there. We just exchange 5A. Okay. And we also see the cycle count there. So it takes less than 1 microsecond to send such. So reverse engineering, SerDes data link. So yes, because we speak only about the software part. In fact, it's interesting to know what happens before. Okay, and why do we need to know that, the data links, how it works? Because it's not documented at all. And it's because we want to interface it potentially with FPGA. Okay, external world. So there, I thanks to Andrew Sonnenberg, because he helped me when I provided him some oscilloscope capture to figure out it probably serial data specification is based. So everything is encoded with such specification. So it's an interesting point. So now, let's see the other big point. It's related to USB3. So USB 2 was clearly documented with everything, the source code, no blob. But USB 3, you have absolutely a big blob. So a big problem, as you don't know what happens and even how it works internally. And of course, you cannot fix it because you don't know how it works. So, So yes, it's based on CH372 device example provided by WCH to reverse it. So it's mainly a USB3 device bulk. It's the most important or interesting mode because you can interface with any PC computer, and it even supports burst. It's specific to USB 3. So firmware reverse engineering about that part, we see in the code that there were a lot of basic small functions to reverse. So the device init, the switch power mode, the device set address, etc., etc. All are quite easy to reverse, like you can see. Okay, again, you need to research a lot because you see all that mess. In fact, at the end, it just SSTX control in it, RX control in it. Thereafter, you have the USB status. Okay, USB control, link configuration, and so on. Well, the value there, we don't know what is it. It's the only problem. And there we have a loop. Okay, so there is quite basically the USB 3 device in it because the chipset works in two modes, in host mode, in device mode, but we will focus only on device mode. So now, check the blob USB 3 in set, for example. Let's reverse that. So it's quite simple when you see there is not a lot of instruction, but it's quite a mess. You see, there is concat and with things we don't really, so we need to check a bit more, and we simplify that exactly to that. It's endpoint multiplied by 4, and then you do that. It was quite the same there. So the reverse engineering is quite easy anyway on such function, thanks to Ghidra. So the final quest, yes. Yes, because it's not easy for all things. And the most hardest one is this one, the USB 3 IRQ handler reverse engineering. Why it's complex? Because it's a critical function as it's a main state machine doing link management packets, mainly some callback, and the management of all endpoints, like we see there, a USB device has multiple endpoints. So endpoint 0 is a control pipe on all device, and such other endpoints are user configurable endpoint to communicate and transfer data. And such things are all managed by the USB 3 IRQ handler, okay? Especially USB 3 standard request, non-standard request are managed by endpoint 0. So there, one complex function to reverse. Main issue, big matching state, let's say. No details on register, only register name, few defines. A lot of research, of course, reading also the USB 3 specification, which are quite complex. So hard to factorize all that mess. Yes, it took a lot of iteration, rewriting, rebuilding, checking the ASM code, multi-time, until magically it works. At least doing USB 3 enumeration. Because when you are rewriting such type of function, as it's the main function, you don't have anything if there is one bug. No USB 3 enumeration. And of course, impossible to debug. Why? Because USB 3 is so fast that during enumeration you have few microseconds. So you cannot break or even add some trace on UART because USB enumeration fail again. So it's quite crazy to debug that mess. Even with USB 3 analyzer, it doesn't help at that step because when you have some bugs there, it doesn't even, for example, send the data or a lot of things happen. So yes, other option could have been to use HSPI. It's a parallel bus, or the CERDES to have some real-time DMI trace. But yes, requiring also USB 3 to retrieve such trace on the PC. Like it's a chicken or the egg dilemma. Yes, we cannot have both because I need USB 3 working. So yeah. So let's continue on the big IRQ handler. Like you see there, it's more complex. Clearly more complex. It doesn't even enter in the slide. And it's more than 260 line of codes, of pseudocode. You see there, tons of register. We don't know what is it. Okay. So we will analyze.
I'm afraid you'll have to jump to the conclusion.
Yeah. Okay. So yes, we see different parts to be analyzed. And then when we have understood better how it works, we have the final code. And it works by luck. So yes, it's a final board with a USB3 where you need a cable. And there also a little hint about when you reverse a binary. I will check you that on a GitHub issue 2466. It's an important point to understand what is the GP, global pointer on RISC-V. And the conclusion, so yes, so we have designed a board there because there was nothing available. We have done full reverse engineering on the firmware blobs and rewritten them in C for the CERDES. Then we have done the same for USB3 debug bulk. Donc, firmware is fully rewritten in C, an open source, of course. And we also provide a hint to do the firmware reverse engineering on a binary about a global pointer. So that's all. Thanks to contributor with that project, which is open source. There, it's a Hydra USB3 on GitHub. So thanks to Hans Bayer, which helped on some reverse engineering on the bootloader. I don't have represented there. And Jules Mazelbaz, which is here, which helped a lot with the flasher, because he wrote everything at the start in from scratch in C, from Rust code. Okay, and you have the BSP there. It's the driver, in fact. Okay. The
Thank
bonus.
you very much, Benjamin.